not fitting the data as well, right? And then maybe you'd say something like this one meets in the middle. It's degree 3. It's not too complex a model, but it's fitting some trend in the data pretty well. All right, so okay, and so this is the topic of today, and we're going to talk about a technique called cross-validation. All right, so I'm going to take the screen down. Any questions about this you want to see before I'll do a demo at the end of the lecture as well. But, all right, so any questions about this? All right. Okay. So I'll start by just saying, basically the question we want to ask is, how good is the like how good is the model, right? And so this cross-validation in kind of the world of how you analyze kind of some model is newer than kind of the idea of like statistics. So doing statistics like a t-test goes back, so roughly 100 years to like Fisher or so. And so in a lot of parts of science, doing calculating the p-value with the t-test or some other sort of statistical test is still kind of the dominant way of testing. So like how good is a model? And so this is important because we're going to have multiple models, and as p gets larger and larger, the fit is better. So we can't just say, how small is the sum of squared errors between our data and so the model, right? So if this was true, then as I keep increasing the value p, this sum of squared errors is going to keep going down and down. But at some point, it's going to start doing something silly. It's going to fit the data, but it's not really. It's not necessarily something we're going to trust. It's going to overfit onto the data. Okay. So if you're going from the statistical point of view, you could say, I can say, look at the residuals, right? So I have this set R1, R2, up to Rn, where Ri is going to be equal to the absolute value of the model of xi minus yi, right? So I can look at this set of these residuals, and baked into this sum of squared errors measurement of the error that we're doing, and this was how we solved for the model for linear regression or for polynomial regression the same way, because we started by linearizing it, is that these should follow some sort of normal distribution. There should be probably without the absolute value here. Let's call these tilde. Okay, so there should be a normal distribution with mean 0 and standard deviation sigma, or the variance of sigma squared. Okay, so I can assume that these come from a like normal distribution. And so maybe how good the model is how well the data actually fits this normal distribution. I can say if it looks like they come from a normal distribution with this value of p, then maybe that's a good model. Clearly, as p increases, sigma is going to decrease. The variance of the errors will decrease because the errors are going to go down. Minimizing sum of squared errors is actually minimizing, making this as small as possible. Okay, but I could say, well, how good is the fit? If I'm overfitting, maybe some things have error 0 and other things have more error. But there could be multiple values of p which actually look like they're a good fit here, right? This is kind of, you know, not so quite doing the right thing here. All right, so this is maybe the older statistical view of how good is the model, and neither of these are what cross-validation is doing. Okay, so cross-validation is kind of a newer approach, because when kind of statistics was invented and popularized and in science for a long time, it was useful because it got the most out of your data. If I didn't have a lot of data, then I wanted to try and use it as analyze everything I could possibly do about it. But so in kind of modern data analysis, we have lots and lots of data, right? So we have lots and lots of data. So n is so big, right? The number of data points we have is big, and this means that we can actually, we don't need to use all of the data to try and build a model, and we can hold out some data to try and evaluate how how good the model is. Okay. The other important aspect of this that is necessary to make this work is that it's assumed that the data is IID. Okay. So it's assumed that every data point, so each data point in XY, each data point is drawn, there's some unknown distribution that this data is drawn from. And they're all drawn IID from the same distribution. Okay, and so this is also really important. What this means is that we're going to have some large data set, X and Y, right? So think of this as N. Okay, so we have lots of N. And so each of these rows is assumed to be drawn IID from some unknown distribution. Right, so I've got these rows here. Okay, and so what I'm going to do is I'm going to think of, I can select some subset of these rows at like at random, okay, and so this will be the test data. This will be X test, Y test, okay, and then everything else is going to be the training data. Okay, so I'm going to split everything that is not the test is a training data. Okay, so and it includes the X values and the Y values here. Okay, and so we're going to have the property that X is going to equal the union of X train and X test, and similarly Y y train and y test. Okay, is a union of these two, and they are also going to be disjoint, right? And also x train intersect x test is going to be the empty set, and similar with y. Okay, so it's a disjoint split, and this split is done at random. So we're going to split at random, and what this means is that x train y train is also going to be IID from this distribution, and also x test y test is also going to be IID from this distribution. Okay, so because we have so much data, we can split it into two parts. We're still going to have enough data to train with that's separate from the testing data, and they're both going to be IID from the same distribution as the full data set. Okay, so we can take our data and split it in this way. Okay, and so then what this is going to mean is that we can now separate. We're going to do the training on the training data and the evaluation on the testing data. All right, so I'll step through kind of an example of actually doing this, but so kind of this is kind of the mechanical part about how we split this up. The key thing to take away is, let's go back over here, is instead of how small is SSE, looking at the residuals and try and analyze them. The thing is how well the model works on new data. Okay, so I want to evaluate the model based on how well it's going to work on if I get some new data that I've not seen before. Okay, so if you remember with the first example I put up with regression, where I had the heights of a bunch of people and I was building a model of what the weight is, and I had this leftover number which was 69 inches, and I said the goal was to predict how heavy that person was going to be. We did not have the weight associated with that person. We just needed to try and predict what that weight was of this new person. And how well we should gauge our model is it's making these predictions for us, is what the model's doing, and we want to measure how well it works on this new data. Okay, so this concept is called generalization. Okay, so how well does it generalize to new data? Okay.
Quick question, go back.
Yep.
So the sum of squared errors and the residuals. The sum of squared errors is just the square of the residuals, right? And then summing them up.
Well,
so both kind of looking at residual basis.
Right. Right.
Okay.
Yeah. So this one is problematic because as we keep making p bigger, then it's the error is just going to keep getting smaller. But that's not really the right answer, because if I look at something that has a really high polynomial, it's not going to do well if I try some new data points, right? I mean, it's possible it does well, but it's probably trying to do too well on the data it has, and it might not do better on data which is new, right? Where this doesn't really tell us about if the data is new. It just says Well, we kind of used this proxy assumption that we had normal noise distribution, and so that allowed us to get this kind of this clever, easy to solve for solution of the model. But like this is following too close to this proxy function we're doing. When really what we care is how well does it work on the new data. We can measure this with sum of squared errors and in some ways before. That's a reasonable thing to do. But this is not necessarily tied to sum of squared errors. This okay, and this is how well does it generalize to new data. And so we can use cross-validation to do that by saying we're going to train on part of the training data. And then the test data is we're going to pretend this is new data, right? If we had instead said, well, these data came in some order, and this was the testing data, and this was the training data, generally you should split randomly. That's why I took care to draw it up here like this. But if we thought this was data that came at the end, then we're actually seeing how well it came out new data after this point, if this was the testing data. Right? And we actually have the y values here, so we actually know how well we're doing.
So let's say that like you're a business and you want to predict how future sales are going to come.
Right.
Would it be okay then to not take it randomly? Because it's like, how well does my past data predict data that came in the last quarter or something like that? Does that make sense? Like,
yeah. So if you're worried that your data is changing over time, then you're saying, well, I don't want to just predict on the most recent data, or maybe I want to predict on the most recent data, but then you'd also like to use that data to train your model as well, right? The most recent data is probably more indicative of what's in the model. So probably what you would do is you would take all of your data and you'd weight it, say how important it is inside of both building the model and evaluating based where the more recent things are worth more in terms of the evaluation and the training, and then you'd still select them randomly. And you maybe, if these are weighted small enough, I can maybe even ignore them, sort of thing. But I would still select randomly because you don't want to put bias into it based on the timing aspect. This is, yeah, it a little bit violates this IID assumption, which is kind of necessary for all this to conceptually go through, but it's what people will do anyways. That's kind of the standard thing to do because we don't necessarily have a much better way of dealing with it. There's probably some way you can rationalize this approach by saying, well, the variance is higher on the older data against our new model, but still unbiased, and so by having a higher variance, it ends up creating a lower weight. And so forth. And you can use Bayesian statistics to probably rationalize it that way. By how you change the prior. Okay. So let me make this a little bit more concrete. What we're actually doing. Okay. So. I'll make it concrete on the board without actual numbers. It's hard to write numbers on the board, but we'll go and we'll do an example on the computer. So step one, I'm going to split x, y randomly into the xy test and xy train. Okay? So step two, I'm going to now train a model. And alpha, say we're in this case with linear regression, it's going to be x train transpose x train inverse x train transpose y train. Okay. And then step 3, I'm going to evaluate. Okay, it'll be something like x, y in x test y, and then I'll do something like squared of the model alpha, and this came from here, right? So that fx alpha, right? So now I'm going to evaluate, and I'm going to get some sort of score. Okay, and this score will tell me how good this model is. So if I use this sum of the squared errors, it's just going to give me some number, and the smaller the better. So this is going to give me the sum of the squared errors. What's a little bit more in what's a little bit more interpretable is going to be called the root mean squared error. This is you might just see this called the RMSE, and so this will be 1 over n, say, test of okay, and this will be m alpha x minus y squared. Okay, so the root refers to the square root around the outside. The mean means I've taken an average, so I've done a 1 over n in front of here, the number of testing. So this is now the average squared error, and then I took the square root of that. The advantage of this is this has the same units as y, right? So this number will be more interpretable. As I change the number of test data points, this number should roughly stay the same. And as the number of test data points gets bigger, it should be converging to a fixed value, right? So what this means is that if I go back to the second thing over there and look at these residuals, but I just look at the residuals on the test data, and I look at the root mean squared error, then this should be converging to the true error on new data as the number of test data points is getting larger. And by kind of all the central limit theorem arguments that we talked about earlier, we can kind of look at how fast this is converging. We can kind of say, well, if I can, you have to estimate what the variance is here based on the data, but you can kind of get an estimate of how fast it's converging by looking at the variance and then applying like a Chebyshev value. You get a sense of how big does this need to be in order for me to get an accurate estimate of how well this model will work on the new data. Okay, so you split it randomly, you train on the training data, and you evaluate on the testing data. And then I would evaluate using the root mean squared error. Is going to give you something that's going to be that's going to be interpretable. As you get more testing data, this is going to converge to the right answer at a rate that we can pretty much understand if we can estimate what the variance is of this error. There's kind of a question you should probably be having in your head, how big should, say, n test versus n train? How much should I put in the training set versus in the testing set? Right, so I claimed that n was big, so we have lots of data, right? So we have a lot of it, but so how should I split in between these two? Yeah.
I'm guessing like so you can say that like n test plus n train is equal to your overall n. So maybe
right.
Like 40, maybe like 40 for the test and 60 for the train.
So sure. So okay. So I heard 60% for the train, 40% for the test. I'd say this is usually a little bit larger on the testing part. Usually, I would say, usually it's, say, sometimes it's as big as 1/3, and sometimes roughly as small as 10%. I would say it's usually in between these two, right? Where you'd have a pretty small amount for the testing part and a larger amount for the training part. You really care about building as good of a model as you can. So what's a rationale for splitting this? One is people are often people are greedy, and they want the model to be as good as possible, as optimized as possible. So they don't want to give the part of the testing data you're not using to make your model any better in some sense. You're just using it to evaluate it. So I'd rather put more stock in the training if I can. And you had the right idea with 60-40 split, but usually it's, they're even more greedy. Another way of thinking about this is for the testing data, I only need enough data to converge my estimate according to some central limit here. Right? So if my n was growing, if my size of my data set n was getting larger and larger, the number of data points I need in the test data doesn't necessarily need to grow. Okay? I'm going to get the same accuracy in my test data with 1,000 test points, no matter how big is my training set. Okay, so the reason you still kind of see these percentages that are growing somehow proportionally onto the sizes is, at least in research papers and these contexts, so like Kaggle, there's usually this kind of real big push to try and drive make the models better and better and better. And there's some score at the end, the root mean squared error score. How low can they get this? And if your testing data is a fixed size and the error is getting smaller and smaller, your accuracy on how good that error is, it stays fixed. So once you get below the accuracy of how good your testing data is, then the numbers are not meaningful in comparing so like two different models anymore. So you at least need enough data to compare two different models if you care about that. So like in reality, kind of if you're getting, I don't know, like if the difference is kind of very small on the root mean squared error, that you have 1,000 data points and you can't really tell the difference up to the error that you're getting in the testing data, it's probably not going to be a very noticeable difference in the models. You're probably kind of like optimizing probably more than you actually need to, is my view on it. So in practice, it's probably okay to fix the test data. Once you get more than, say, 1,000 data points in it, you probably don't need to make it any bigger. If your total n is something like only like 100 or 300, something like that, then one split like this probably makes more sense. you need at least enough data so you trust the testing results. Okay, and then once you have enough to trust the results, put the rest in your training. Okay. The other thing that's kind of going on here is that why is the test, another reason why the testing usually has less data in the testing set is that to estimate the testing data, I've got a pretty simple random variable I'm estimating here. Usually it's a one-dimensional random variable I'm trying to estimate. The error is usually just in the y value. Whereas the model, you can think of the model as also converging towards the right model as I get more and more training data. But this model might now be more complicated. The alpha is a higher dimensional vector. And we didn't talk about it in class, but as you can imagine, there are these Chernoff-Hopting bounds or Chebyshev sort of bounds that deal with these estimating quantities which are going to be higher dimensional. And these might require more data in order to get the same sort of estimation. So if I think I want my training and my test data to be converging at the same rate, as I might need more training data to learn the right, more complex model than I do just to evaluate it. Okay, so that's kind of roughly the rationale of these, but these numbers are kind of historical, and people have used between 10 and 33% for a long time, and so these are probably like looking back at what happened, why people chose those numbers, but these kind of seem reasonable as a rule of thumb. Anywhere in between here is probably fine. Yeah.
How do we know if that inverse matrix exists for X train transpose X train?
Oh, okay. So yeah, is this going to be full rank? Right, that's what you're asking, right? If I reduce my training data, then it might not be full rank here. And this is indeed a problem. It can be a problem. Now, the first answer to that, and that's the answer we need for this class as opposed to the next class after this one, is that really in order to be training a model that complex with D variables, you probably need n train, the number of training points, to be much larger than D. If n is much larger than D, this is probably going to be full rank. Okay, this is a D by D matrix. And if n is much bigger than D, it's probably going to be full rank because there's probably some noise in the data collection process. Okay, so for this class, that's the answer you need. There's stuff that's in the book that we aren't going to cover in here. So there's a technique called ridge regression, which is adding a regularization parameter onto the regression. So instead of minimizing the sum of squared errors, right, someplace, it's saying you're minimizing the sum of squared errors plus some penalty term for having large coefficients in alpha. Okay, now there are various ways to do this, but you don't want very large coefficients here. They correspond with unstable predictions. That's all I'll say for now. It turns out in the optimization, the ridge optimization, what it's doing, ridge, it's going to have some parameter lambda here, and then the optimization alpha lambda is going to be x transpose x plus lambda times the identity matrix. This forces it to be full rank, x transpose y. Okay? So before I do the inverse, I add this identity matrix times some small parameter lambda, which you have to tune somehow. And this forces the matrix to be full rank before you invert it, and makes this predictions more stable, and tends to give you smaller coefficients for alpha in some way that we won't. You can peek in the book to see more about this. But this is the other kind of longer answer of what you do if this inverse does not exist.
I can't remember where I was looking. I think it might be our implementation of like linear regression or potentially or like, but they also have like, you can find this like near inverse operation.
So the pseudo inverse?
Yeah, I think that's
Yeah, so you can do the pseudo inverse as well. That'll be a more, it gives you something that works like an inverse for this purpose if it's not full rank. We'll see what the pseudo inverse is later when we talk about singular vectors and eigenvectors. It's basically, you take the unstable parts of the inverse and you kind of set those to 0. Ends up being what the pseudo inverse is. And that's another way of solving it. This is the correct way of doing it. But there are different versions of correct. But this has other nice properties in addition to ensuring that the inverse will work. Whereas the pseudo inverse might do something unpredictable in those sense, but it will work in general. So if you write code with the pseudo inverse, then your code will never throw kind of an exception or have an error for that, but it won't necessarily give you a model which is. So we're doing good. Okay, so I started the class saying with a problem where we have this model and we can have this value p, and as we increase this polynomial degree p, the model seems to fit the data better and better and better. Okay, and then I kind of said, how good is the model? We talked about these ways, and we came up with generalization and cross-validation. Okay, so how do I choose the right value p? Okay, so we should come back to this question. This is what motivated all of us.
You could just try a bunch of different p's and then follow this process and go with the one that has the least root squared error.
Sure, yeah. So good. So let me write it around here. Basically, what I want to do is I want to take steps 2 and 3. And I want to put these in a kind of, I want to put these inside like a for loop. For p equals 1 to let's say k, right? You can pick something bigger than you think. And so we're going to train a model m alpha p. Right, and this will be, I'll do some polynomial expansion on each of these. And so I'm going to train an alpha p for every value of p, and I'm going to get a score p, and then step 4 is going to be select m alpha p with smallest sum of squared errors of p. Okay, so I just I need to do kind of brute force checking all the values of p. Right, when it's discrete like this, this is fine. I've got k different possible models I can choose, right, up to some choice of k. I don't know what the maximum is, but generally what's going to happen is that the sum of the squared errors is going to start probably maybe reasonable with p equals 1, and then decrease, and then it's going to start increasing again. If I make p too big, I'm going to overfit to the data, and my error is going to get worse and worse, actually. And so when I start seeing that, I can kind of stop. So I don't necessarily need to preset this. I can keep searching until.
Is it possible that you find a different P depending on how the training and test data is split?
Yes, that's true, yeah. So one issue is definitely that if it's a random process how we split the data, and I might get a different answer different times I do it. Right, so if you're dealing with a pretty small data set, and I'll show an example with 10 data points so we can see what's going on. It'll definitely be the case if I change which points I select, I will get a different value of P. But in general, if I have like, remember n was big was kind of our underlying assumption here. And then, so then if n is like 1,000 or 10,000, it hopefully should map. And if it does and it's close, so I'm going to say if it's close, choose the smaller p. Okay, so in general, you want to choose the simpler model. There's this KISS principle. So I think it's like so it's like keep it simple, stupid. I think is what that stands for, or like Occam's razor. I'm not sure if I'm spelling Occam's razor correctly. Occam's razor, but basically the simpler model is better. Okay, so if I have a choice, and it's actually pretty close, right, and the sum of squared errors are pretty close for two models, I'm better off choosing the model which is simple. These will tend to generalize better to new data. Maybe it's because my data is only in a small range, and I'm worried about extrapolating outside that range of the data. And in one dimension, this is hard to kind of, it seems like you should really only trust it in the range, but in higher dimensions, it's hard to define what is inside the range. I think we mentioned this in an earlier lecture. And so kind of the simpler model is going to tend to extrapolate better. Not necessarily, but in general, this tends to be true. Yes?
So if you have like a multiple linear regression model, and you have like 10 features or something like that, does that just mean the one with like a smaller norm, or like how would that work exactly?
Yeah, so okay, so with multiple, so like linear regression, I haven't introduced a parameter that you can actually choose. I could do a polynomial expansion on those, right? I could make it, usually with multiple linear regression, the model is already powerful enough, you might not need to do a polynomial expansion. You do only start with that with low dimensional initial data, typically. You might try kind of a like quadratic expansion. What happens though is you might get D might be getting closer to N, and this tends to happen. And then these things like ridge regression is going to start being useful. Okay, a simpler model is then going to be the larger the ridge term is going to give you smaller values of alpha. And so you can also use this to try and choose this value of lambda here. And this now is continuous, so now you need to search over a continuous space, and it's not necessarily convex. So you kind of have to, there's another version called lasso, which I won't get into here, but this will actually force some of the coefficients to be 0 exactly. This will just make them small in general. It makes the L2 norm small. The lasso will force some of them to be 0, and then you're basically saying these coordinates, I can build a model without them. So I can do a polynomial expansion. I don't need all of those quadratic terms, so some of them get set to 0, and the kind of some issues with the units when you do this, so I don't want to get, there's some other complicating factors, but in principle, if I have a very big multiple linear regression system, then I can do this lasso version, and that will actually drive some of the coefficients to 0, which means I don't need some of those values of D. And that's how you can solve it when the dimension D is approaching n, or even larger than n in some cases.
Can you explain what P and K are here?
Yeah, okay, so P is this is the degree of the polynomial, right? So this was, I built a model up to degree P. So if it's the fifth order, P would be 5. Right, and K would be a max degree to consider. Let's say I'm not going to have more than a 10-degree polynomial. Probably not 10, but I know it's not going to be larger than 10. So I'm going to stop my search after 10. And then I'll just build every model from degree 1 up to degree 10, and then I'm going to take whichever model gives me the least sum of squared errors on the held out test set.
So I was wondering, so like when you're always checking from P to K for any class validation using any prediction model, like a machine learning model, I was thinking of having a max of a minimum. But is that not always the case? Is there certain situations where there might be multiple minimums?
Yeah, there's nothing that's forcing this to be convex. We'll start talking about convexity on Wednesday, in fact, but convex basically just means that it will go down and then it will come up again. And there's nothing that isn't forcing it to do this. There's no reason it has to be convex. They typically are convex, okay, but not necessarily. I have seen, it's often assumed that things like with lasso, this lasso version of this, which is you can make more discrete than the Scridge version, and there are kind of a bunch of discrete different values you could choose, and you can actually compute all the different discrete values, which might give you potentially the correct answers. And it's a long time assumed that there were a linear number of different things you needed to check. But someone came up with an example where you need to check an exponential number, right? It could be possible you have to check an exponential number of different, and they could have local minimum in them, and it's a mess. Okay, but in general, it's going to act like it's convex, so you can start going down, and then it'll start going back up, and when it starts going back up far enough, you can say, okay, I can stop. That's generally pretty safe to do. It should act, in general, for almost every data we've seen, up till a few years ago. I'll tell one more story in a second. It's always kind of, as you increase the complexity of the model, it found the sweet spot and then started getting worse. You started overfitting. Okay, so in this class, this is kind of where we'll stop. There's kind of been some really amazing insights the last couple of years with these deep net models, these deep neural networks. If you don't know anything about these are models. Usually, they can be used for regression. You can kind of think of them as doing something like the polynomial expansion, but much more complicated, and there's layers and there's stuff I'm not going to get into. But I think you can build more and more complex models here. And what's kind of amazing has happened as starting a few years ago, people realized that they were not overfitting, even if they built more and more models, which are getting more complex than we thought. We would have enough. We would have enough data. Okay, we thought there was, if I only have 1 million data points, if I have a billion data points, there's kind of these things like, well, there's something called VC dimension, which tells you roughly how complex your model should be based on how many data points you have to predict error. And even with a billion data points, your model should only be able to get complexity of maybe 30, something, an arbitrary number. But neural nets are much more complex. And there's been this weird phenomenon, and there's a paper just like last year, I think, which showed what happened is that this kind of goes up, and then it starts coming back down. Okay, and people realize this when you build these incredibly big models, and you have enormous amount of data, that the more and more complex models tend to do even better here. And these fast neural net models, which are getting kind of amazing accuracy, are basically way off here. Okay, they've broken this paradigm of cross-validation in some way.
When it comes down again, does it usually come down to like the same?
It's usually lower than before.
Oh, usually lower. Okay.
Yeah, which is what's amazing about it, right? People, why are deep net models doing better than all this machinery from the past 30 years, right? And this might be the answer, right? It's still, this is a paper from like 1 or 2 years ago. People are excited about it, but it's not, I don't know, I wouldn't say it's set in stone yet. What is saving it? There's some hypotheses. Some is that they're somehow the learning process, and we'll get into kind of closer to how they're actually learned. It's not by doing this inverse trick. It's doing some other stuff with gradient descent and other bells and whistles, but it's somehow implicitly biasing towards a model which is simpler. Okay, so there's a huge space of models, but it's somehow biasing towards a simpler one. And the data seems to be big enough that it's okay to overfit, right? That we have so much data that in the space where we're predicting, we kind of, the data, we're not ever extrapolating anymore. So it's some combination of, we're not really extrapolating because we have so much data, and there's some kind of inherent process in the system which is keeping the models simpler, even as we're learning. Okay, and some of these are things like this ridge term. This is kind of the first insight into it, but there's other stuff going on which is harder to quantify. If you take the data mining class, you'll see why this ridge term is doing what it's doing in a way that's meaningful. But these other things like dropout and stochastic gradient descent, which we'll discuss, but we won't understand why it works in this class. Okay, so this is a kind of newer insights, but for now we'll just talk about cross-validation. For most of the data sets you will deal with, unless you're at kind of a company that has lots and lots of data, more than I probably have access to, you probably won't even see this. People generated it in some synthetic ways, but otherwise you just need enormous amounts of data to really verify that's what's going on. Okay, so then, so to keep the class back, let's pretend it looks like this. Okay, so for the past 30 years, that's what the picture is. Okay, good. So did I cover everything before we see some data? Yeah, let's go look at some data, and then there might be some more stuff I can say. All right, so to give you a preview, I'm going to show an example with 10 data points, which is too small. We can talk about afterwards what you should probably actually do with 10 data points. But okay, so I'm loading. Let me make it a bit bigger. Good. Okay, so I'm loading. So like NumPy that has arrays, the linear algebra package. And then I'll use a command from SciPy to do the polynomial regression, because this one has a really nice kind of way I can change one parameter without changing the rest of the code. Okay, and then some plotting functionality. Okay, and then load some training data. I've already randomly split my X train data and X and Y training data and X and Y test data. I have 7 and 3. Okay, so a 70-30 split. And this is too small to really trust, but I've chosen the data so it looks nice. And then so let's plot it. The testing data, the training data is in blue, and the testing data is here in green. Okay, so it seems reasonable, even though it's only 10 data points. This will be good to show what's going on. Okay, and and if you're doing this, even if I don't ask you to plot it, go and plot it. You're much more likely to not, the plotting really helps you verify that you didn't make a stupid mistake along the way. Okay, it's a really useful way to because it's very easy to make mistakes and not know what's going on. Okay, so I did a polynomial fit. I'm using this from SciPy. It has this polyfit with the parameter p. It gives me these coefficients. I plug it in here, and it gives me p plus 1 coefficients. And then this takes this in, and then does the gives me this curve array, and then I will plot this line and the data. Okay, and now this is the linear fit through the blue points, right? And I can then calculate the residual vector and the sum of squared errors is the norm of the residual vector squared. That's this simple way just to compute it. I'm taking a square root and then squaring it again, but fine, whatever. It's easy to write the code for. Okay, so this is the residual vector 6, 9, 11, and this is the sum of the squared errors. It seems smaller than it should be. Oh no, sorry, this is the fit. This is not the residual vector. So that's why. Okay, so minus fit minus e, right? That's on the right. So I'm doing the this is my model f fit, and I put in the test data and I subtract the test data. Then this is my residual vector, and this is the sum of the square roots. I'm mainly dominated by this first one. If I go back and look here, this was this first data point, and this one has a larger.
If you drop the polynomial to 0, will it just give you the average?
Oh, I'm not sure. Let's see what happens. I'm guessing that's what's going to happen here. Yep, that's what happened. It just gave me the offset. So I just I raised everything to the power 0, and that was it, and that gave everything. Yeah. Good. Okay, so this will do even worse, I'm guessing. Yeah, so 36, right? This is even worse squared. Sum of squared errors. Okay, let's change it to 2. Okay, 2. We plot it. Now this curve's looking better. It's actually fitting the green data better, and the sum of the squared errors is now less than 1, 0.9. Okay, it was like 5 before. Okay, so I've got a better model on the test data. Let's go back up to 3. Okay, 3 is doing, okay, it looks pretty similar. Okay, and the error is slightly larger here. Okay, so so let's see what happens with 4. With 4, it's going to look like this. All right, so I fit the blue data better, but now the green data worse, right? And the error is even back up to 3. And let's just go back to 5. Okay, now I've hit all the blue points exactly, right? But the green points, it's probably doing worse here, and it's backed up to 33. This is roughly as bad as doing the 0 degree. Right, so, okay, so what was the right degree? What should I choose here? 2, right? 2 was slightly less than 3, and someone had a question, what if I select a different data, that might be different. The 3 degree model might be, what if those numbers had been reversed? if 3 had 0.91 and 2 had 0.93?
Stick with 2.
I would still stick with 2, right? If I look at, let's say that this model was still, if I just look at this, right? This is the 3-degree polynomial model. There's nothing that looks like a 3rd-degree polynomial on it. That should have an inflection point. And probably there's another inflection point that goes up there somewhere. But there's only one kind of, it looks like it's only degree 2 here. So there's no reason to pick a more complex model, especially if the error is not significantly better, right? Right. So even if the error was slightly smaller for 3, and I think probably the first time I did this data split, that was actually the case, and then I played around with it so that it was cleaner, but so that the 2nd degree had smaller error. But I would still pick the 2nd degree model, especially if you only have like 10 data points, right? You don't want too complex a model for only a small number of data points. All right, and if you haven't been seeing, I've been posting these IPython notebooks, links to the collab files on the homepage for the course, so you'll have access to this, and might be useful part of the way towards what you need to do for your homework. All right, any questions on this? You want me to do anything else with this data? Or change the data, see what happens?
Would we add like a super far outlier to the right? Like a high leverage something?
Okay, so let's put the X in the training or the testing? Let's do the testing in the training set.
Training, yeah.
Let's do 20 and then let's say 14. Okay. Okay, this is what the data looks like. I think I have my, this one, I don't know if my line will go. Yeah, I fixed my line space. Okay. This goes up from 0 to 10. What do I need to change? Let's go up to 20. What do I need to do here? Good. All right. So now the 3rd degree model gives me the parabolic part on the first part, and then uses this 3rd degree in order to hit this last point up here. Okay. So it's using, this part is probably only needs degree 2, but to hit these and that one out there, it does that. Where if I did p equals 2, then it's not going to hit these two points right here as well. Yep.
Is it common to only use integers?
Oh, for the degree? Yeah, that's common. There's no technical reason you couldn't expand to like other degrees, right? I could, but think of if you remember, you're building a model of a p plus 1 degree matrix, right? Dimensional matrix. And so I could do half degrees in the model and do that expansion, and it would give me a more complex model. It's not very common, but it would technically be that's feasible. I think everything would work the same way. So you could do that if you wanted to, but I don't know if I've ever seen that happen. I mean, you can do other things, like I could put a sine of x as one of the expansions in there as well, right? You can put any function you want to give you a new column in this matrix that you're expanding, and then you're running the multiple linear regression. So I can put a square root, which is a 1/2 degree, a sine, a logarithm, And this is how you could fit more complex models. Right? It doesn't give you coefficients inside there, but it gives you parameters inside there, but it gives you coefficients in front. Okay. So cool. All right. So let me say one more thing. So when you have 10 data points, this is not what you wanted to do, right? This is not the right thing to do for 10 data points. You know, there were two things this was predicated. One was n was big, and two was this IID assumption. Let's say you still have the IID assumption, right? The data is coming from some unknown distribution I'm trying to model, but I only have 10 data points, right? This happens. I have some friends I've worked with who study like the morphology of like human brains, and so they want to get CAT scans of people at 3 different times, and it's really hard to get that data. You have to get people to agree to do this. Everything costs like several $1,000s to run one scan. So these data sets are really expensive. They may only have 10 data points. Okay, and they want to build some model like a regression model. First thing, if it's complex like that, you probably need to bring in a bunch of like domain knowledge in, and say something about maybe I do want to do a polynomial regression, and I'm going to assume I know some coefficients from the underlying biology of what's going on, but there are other ones I want to fit, and you might use that as a starting point. But the other thing you do not want to only train with only 7 of your 6 or 7 of your data points. You may want to use as many as you can. But I still don't necessarily want to try and do this. Look at residuals. These models still aren't quite right. I still want to do some generalization experiment. So how would I go about doing this? Let me put the screen up.
So what are you trying to predict in this example?
So I'm still doing cross-validation. I still want to know how well a model generalizes. And just in this example here, I only have 10 data points. So I have a small number of data points. Right, so now assume now, right, I want to do something similar. I want to do something like cross-validation, but n is small, right? So instead of n big, I want to say n is small. Okay, I want to use as much training data as I can in order to build my model. Okay, so what I'm going to do is I'm going to say that I'm going to make n train equals n minus 1 and n test equals 1. You know, the smallest I can make the test set. Okay, the problem with this is now the test set is not a good indication of how well I'm doing. Okay, so there's this trick called, there are 2 important things I want to say. So leave one out. So LOO cross-validation. And basically, I do for I equals 1 to n, I'm going to build the test set is equals to set minus xi, yi. This is the train. And the test set. Okay, and then I want to give it a score I, and I want to evaluate on the on the average. Okay, so I'm going to leave one out at a time, build a model as good as I can with the rest of the data, and then get a score by evaluating on the test set based on the model I built, and then take the average of these. So I only have one test data, but I'm using each one as that test data. So there's no randomness here. I'm leaving one out at a time. Now this is expensive as n gets big, because I have to build a model n times. So sometimes if n is big, you do this by splitting 3 ways, and then you average 3 different things like this. And this tells you how to build the best model. Maybe then I pick one of them at random that I've used as the model I actually use going forward. Yeah.
So we wouldn't do this with a bigger n just because it's just so expensive.
It's expensive, and you don't need to, because if n is bigger, I can afford to put more in my test data without a problem. The trained data is still big enough, right? But when n is small, then I need to resort to something like this. Okay, so there's one more important point I forgot to say. Okay, so there are 2 points of cross-validation. It's used for 2 different things. For 2 things. One is to choose best model. I select the P that's the best, right? And the other one is to evaluate the generalization. They say how well we'll do on some new data. Okay, these are separate things. Okay, this is actually part of the training process. This is part of the training. I'm somehow learning what from the data, from the test data, what is the best model. So this is part of training. I can't use the same test data to evaluate generalization because it's biased towards whatever test data I picked in some way. Okay, so if I'm doing both of these need separate test data. These need separate test data. I need to hold out 2 data sets. I might hold out, say, 10% for here and 10% for here to evaluate generalization, right? So I use 80% of my data to train a model. And then there's some parameter associated with it. I'll use a 10% held up test set to choose the best parameter for the model. And then given that I want to know how well it works on new data, I need another 10% in order to do that. Otherwise, the test results from here are not reliable going forward in general. They could be biased towards, well, I picked this parameter because it did well on the test data, but maybe that test data was not totally representative. So I need another independent test set in order to do generalization. And so you don't want to mix these up. So in good kind of machine learning kind of papers, they will hold out 2 data sets, one to help doing the cross-validation to kind of choose the model parameters, and another one to report on how well it should generalize to new data. Okay, and if you have like a Kaggle competition, they will often have 3 data sets. One that they give you full knowledge of, one that they give results back on to that you can try different models to see how well they're working, and then a third one at the end that they say who's the winner. If they're doing it properly, they should be having 3 data sets like this. Otherwise, there are ways to kind of spoof this. People have written papers, and there's code out there that you can actually learn what the test set is by repeated trials of throwing different models at it, and then recover the test set and predict the test set perfectly, but on a 3rd data set, do as good as random. Okay, so you need to have these kind of there are 2 different cases here, and you need to keep separate held out data for both of these.
Is it is that just like overfitting, like where they would figure out the test set? They're just basically overfitting it, is what they're doing too.
Yeah, they're overfitting to the test set. So in Kaggle, usually you can submit one model every day, something like that. But there have been teams that have colluded, so they pretend they're 10 different teams, but they're really one team. And to each of the sub-teams submits models, and then they aggregate these all together at the end to try and do better. And other people have submitted random classifiers for days and days and days, and then use that to combine those together in some way to do really well in the test data. And so if they don't have a count-out set, then you can completely spoof on the system. And these are using more complex sort of techniques than just the polynomial and the polynomial regression we're doing, usually with classification problems, but there's a smaller version of the same effect here. Great, okay, so the homework is out. The quizzes you can pick up after class, and then Wednesday we'll start talking about functions and gradient descent, which is actually how all these problems are solved.